Yay, we're on the internet. So we are just going to take the derivative of exponential functions that don't have that convenient base e, because we know the derivative of the exponential function is just the exponential function. We also know that the derivative of any exponential function is another exponential function. So for example, y equals base 3 to the exponent x. There's my function. And if I were to plot the derivative of y equals base 3 to the exponent x, I would just get another exponential function, but it's been stretched away from the x-axis a little bit because there's some number out in front of it that we just need to figure out. So we're going to quickly go through the proof, which if you've done the preamble, maybe you're already bored with. And then we're going to do one problem that uses the pattern that we derive to take the derivative of an exponential function with a different base. So a couple of key understandings. The log power rule, I don't know if that's what you call it or not, but that's what I'm going to call it. So the log base 10 of 10 to the exponent 3 is equivalent to 3 times the log base 10 of 10. So log power rule, that's what I've called it. Oh, and this rather embarrassing checkup to make sure that you know that the natural log of x is log base e of x. And then the second thing that we've already done a couple times, which is if you take the derivative of y with respect to x, if y is a function of x, then the derivative is y primed. Ooh, if y. If y not? If y is a function of x. There we go. All right, good. So yeah, we're ready to go. Let's take the derivative of y equals base 3 to the exponent x. Let's see what it looks like, and then we'll generalize it. So here we go. Y equals base 3 to the exponent x. What do I do? Oh my goodness, I don't actually know how to take the derivative of this. So what I'm going to use is my log power rule. I'm going to take the log of both sides. And I can do that because the range is positive. So I'm not worried about getting weird results because I go out of my range here. And so the natural log of y, why did I put brackets there? Who knows? Okay. So the power is going to come down in front. Power is a variable this time, but I'm not too worried about that. Now I am ready to take the derivative with respect to x of both sides. There we go. Derivative with respect to x of the, x natural log 3. If I leave out that x, things go south in a hurry. There we go. Okay, let's go over here. Big arrow, connecting the two ideas thoroughly. Okay, this is a function inside of a function, and so I have to use my chain rule. I need to take the derivative of the natural log, and the derivative of the natural log, well, that's easy. This is just 1 over y. And then I have to take the derivative of the inside function with respect to x, and the derivative of y with respect to x is y primed. There we go. I've got my y primed in here, and so it doesn't look like it, but really it is. The natural log of 3 is just a number. It's a constant, and you can calculate it with your calculator. It comes out to, I don't know, 1 and a little tiny bit, 1.09 or something like that. This is really just a number, so I'm taking the derivative of a constant times x, and so that's the same as taking the derivative of, taking a constant times the derivative of x. So this is just the natural log of 3, and the derivative of x is 1. I'm going to isolate my y primed here, and this becomes y times the natural log of 3. But wait a minute. Y is just 3 to the exponent x. And so y primed is 3 to the exponent x times the natural log of 3. Okay. So we can just generalize this if we have y equals some weird base b to the exponent x, and that b could be the Euler number. It's just really easy to take the log then. Then y primed is equal to the natural log of the base times the exponential function. Okay. That was that. Pretty easy, eh? All right. Okay. We're on to the next. Look at that. Maddie's chirping someone else out there. I don't know. Okay. So this is pretty easy. If I have y equals 10 to the exponent x, y primed is going to be the natural log of 10 times 10 to the exponent x. That's also easy. So let's use this derivative into a really calculus-y problem. So let's find the equation of the tangent to y equals 10 to the exponent x when x is equal to 1. There we go. Ooh, lots of magic and mystery in there. Okay, so there's some simple things I can do here. I need to know my x-coordinate. I need to know my y-coordinate. I'm going to use my derivative to find m, and then all I need to do is figure out what b is. Okay, so when x is equal to 1, y is equal to 10 to the exponent 1. There we go. One of the easier exponents to do in your head. So we are at 1 and 10. That's where we want to take our tangent. Now we're going to find the slope, which is just the value of the derivative when x is equal to 1. Okay. Yeah, so basically all I have to do is substitute a 1 in here into this slope function. So m is going to be 10 times the natural log of 10. Good. I have my x-coordinate. I have my y-coordinate. I have this really awkward looking value for my slope. Now I'm going to substitute it into my y equals mx plus b. All those things. And I'm going to figure out what b is. And b is not going to be beautiful, but not all of us were born beautiful, so that's okay. All right. Y is 10. M is 10, natural log of 10. X is 1, and B is yet to be determined. Continue erasing the board. All right, let's isolate B. And so this is equal to 10 minus 10, natural log of 10. B's got a lot of, you know what the B's problem is here? Oh, sorry, there's an extra 10. I was going to say it's 2 10s, but actually it's 3 tenths. Didn't work. Okay, so there's my B value. If you like, you can actually plug this in and calculate it, and it comes out to a number. You can factor it. Not that it's going to do us much good to factor it, but let's factor it because it's calculus. If you're not taking the derivative, you're factoring it, basically. And so we wind up with y being equal to 10 times the natural log of 10 x plus 10 times 1 minus the natural log of 10. There we go. That's it. And so I prefer to see it like that, in all of its raw, all of its rugged, I guess it's ruggedness.